This is the reason your body holds onto fat even when you're eating less. Most weight loss advice treats your body like a calculator. Eat fewer calories than you burn, and fat should disappear. But if you followed that math and watched stubborn fat refuse to budge, the issue probably isn't your arithmetic or your discipline. A hormone called insulin is likely getting in the way. Here's what's actually going on. Every time you eat, your body releases insulin, and while insulin helps control blood sugar, that's only part of its job. Insulin is also a storage signal. When insulin levels go up, your body shifts into storage mode. More importantly, elevated insulin blocks your body from releasing the fat it already has stored. This is basic biology. Your fat cells contain a system designed to break down stored fat, so your body can use it for energy. When insulin is high, that system gets switched off, the fat stays locked in place, so you might have tens of thousands of calories stored as body fat, which is energy your body could theoretically use anytime. But if insulin stays elevated for hours after meals, which it does for most people, your body can't easily access that stored fuel. The key point here is that you can carry extra body fat and still feel genuinely hungry. Not because you lack willpower, but because your body is behaving as if the stored energy isn't available. One study found that elevating insulin reduced fat burning by 85%. That's a massive effect. The real question isn't just how much you eat. It's what's happening with insulin when you eat and how long it stays elevated afterward. This video explains a biological system most people have never had laid out for them clearly, and understanding it changes how you think about fat loss. To understand why this matters, we need to look at what insulin actually does once it reaches your cells. When you eat foods that raise blood sugar, your body releases insulin in response. That insulin travels to cells throughout your body and triggers a chain of internal signals. Here's the part that matters for fat. When insulin is present, it activates a process that shuts down your fat cells' ability to release their contents. At the same time, insulin blocks the very first step of fat breakdown from happening at all. So insulin is stopping fat release through multiple channels at once. What this means in practice is that even modest rises in insulin can significantly reduce your body's ability to tap into stored fat. I want to be precise here because this gets oversimplified constantly. Insulin isn't the enemy. Your body needs insulin to function. The question is how often insulin stays elevated and for how long. A high-carbohydrate meal can keep insulin elevated for 4 hours or more. If you eat frequently throughout the day, you might spend most of your waking hours with insulin levels that actively suppress fat release. During those hours, getting to your stored fat becomes harder. Calories still matter overall, but this helps explain why cutting calories sometimes leaves people tired and hungry without changing their body fat at all. Before going further, I need to be honest about something. The science here is still being debated, and reasonable experts disagree about how central insulin is to the obesity problem. One view argues that elevated insulin from high-carbohydrate diets drives fat storage and makes losing fat difficult. Researchers at Harvard have published papers supporting this interpretation. The argument is that fat accumulation might actually cause overeating rather than the other way around, because the body tries to replace energy it can't access. But there's serious pushback against this view. Kevin Hall, a researcher at the NIH who runs tightly controlled studies where participants live in a research facility and every calorie is measured precisely, has produced results that challenge this model. In one study, even though participants produced 60% more insulin on a higher carbohydrate diet, they actually lost more fat on the low-fat diet, not less. That's the opposite of what the insulin-focused theory would predict. A large trial published in 2018 tracked over 600 adults for 12 months. The low-fat group lost an average of 5.3 kilograms. The low-carb group lost 6.0 kilograms. Statistically, that's the same outcome. The takeaway here is that both perspectives contain some truth. Insulin clearly affects fat storage and release, and nobody disputes that. The debate is whether insulin is the main driver of obesity or just one piece of a more complicated puzzle. The current scientific consensus is that many different dietary approaches can produce weight loss if you end up eating less overall. There's no official endorsement of insulin-focused diets as superior to other methods. What does have solid support or specific behaviors that reduce how much your glucose and insulin spike after meals? These have been tested in controlled studies, and they don't require cutting out carbohydrates or following extreme plans. One of the more surprising findings in recent research involves something as simple as the order you eat your food. Researchers have run studies where participants ate the exact same meal on different days, with identical foods and identical calories. The only thing that changed was the sequence. On one day, participants ate the carbohydrates first, things like bread and juice, then protein and vegetables. On another day, they ate protein and vegetables first, then finished with the carbohydrates. When they ate protein and vegetables first, their blood sugar response was 73% lower. Same meal, same calories. Very different result. Follow-up research found similar effects, with blood sugar responses dropping by about 40% and insulin responses dropping by about 44% just from changing the order. A 2025 study went beyond the lab by tracking people in their everyday lives with continuous glucose monitors. When participants ate carbohydrates last, they spent more time in the healthy blood sugar range, improving from about 79% to roughly 85%. Why does this work? Eating protein and fiber first slows down how quickly food leaves your stomach. That means carbohydrates enter your bloodstream more gradually, which produces a gentler insulin response. What this means in practice is straightforward. When you're eating a meal with carbohydrates like bread, rice, or pasta, eating the protein and vegetables first may reduce the spike that follows. It won't eliminate the effect of the meal entirely, but the research suggests it makes a real difference. Physical activity after meals, specifically walking, has also accumulated solid research support. A 2013 study compared two approaches in older adults at risk for blood sugar problems. One group walked for 45 minutes once a day. The other group took 3 15-minute walks, one after each meal. The post-meal walks improved blood sugar control over the full 24 hours, with especially strong effects after dinner. More recent research found that just 10 minutes of walking immediately after eating lowered peak blood sugar from about 182 to 164 milligrams per deciliter. A meaningful change from a small effort. A review of multiple studies found that light walking after meals reduced blood sugar spikes by an average of roughly 17% compared to staying seated. The mechanism is relatively simple. When your muscles move, they pull sugar out of your bloodstream through a pathway that doesn't need insulin at all. A short walk helps clear some of that blood sugar directly through your muscles, which means your body doesn't have to release as much insulin to deal with it. The key point here is that this doesn't require intense exercise. A 10 to 15-minute walk at a comfortable pace, ideally within 30 minutes of finishing a meal, seems to be enough. Whether this translates to long-term changes in body composition is harder to say because the studies haven't tracked that consistently. But the immediate effect on blood sugar and insulin is reliable. Time-restricted eating, which means limiting your food intake to a set window during the day, has also gotten serious research attention. A well-known study from 2018 was especially carefully designed. Researchers gave participants all their food, so calories were exactly matched between groups. The only difference was whether people ate within a 6-hour window or a 12-hour window. The shorter eating window improved how well the body responded to insulin, and it lowered blood pressure, all without any weight loss happening. This suggested that limiting when you eat might have benefits independent of how much you eat. But a study published in late 2025 complicates that picture. This one also matched calories precisely. When calories were truly equal, the shorter eating window produced no meaningful changes in insulin sensitivity, blood sugar, or inflammation markers. The researchers concluded that benefits seen in earlier studies were probably coming from people unintentionally eating less. When you compress your eating window, most people end up consuming fewer calories even if they're not trying to. A 2025 review looking at multiple studies found modest effects. Average weight loss around 1.9 kilograms and slightly lower fasting insulin levels. The honest reading of the evidence is that time-restricted eating probably helps mainly by making it easier to eat less overall. Whether there are additional benefits from the timing itself remains genuinely uncertain. What's clear is that it's not a metabolic magic trick. But for some people, having a defined eating window provides useful structure, and that structure might have value even if the mechanism is simply eating fewer calories. Stepping back from specific strategies, I want to put all of this in context. The basic biology of insulin and fat is well established. Insulin does suppress fat release. Insulin does reduce fat burning. Nobody seriously disputes that. But obesity and weight regulation involve complications that go well beyond any single hormone. About 40% of young American adults now have insulin resistance. But here's something that surprises most people. 50% of those with insulin resistance are not obese. And paradoxically, fat tissue in obesity often shows higher baseline fat release, not lower, even though insulin resistance is present. The brain plays a role that insulin-focused discussions often overlook. The hunger you feel despite having plenty of stored fat isn't fully explained by insulin-blocking fat release. Another hormone called leptin, which fat cells produce to tell your brain you have enough energy stored, often stops working properly in obesity. So even with high leptin levels, the brain behaves as if the body is starving. One neuroscientist who studies obesity puts it this way: once you start studying this seriously, you quickly realize the brain is running the show. There's also population-level evidence that complicates a simple insulin story. Traditional populations eating high-carbohydrate diets, including groups in the Pacific Islands, Africa, and Japan, historically had very low obesity rates, despite eating in ways that would produce regular insulin responses. The takeaway is that insulin belongs in the picture, but it doesn't fill the entire frame. So what does all this leave us with? First, the feeling that your body is holding onto fat isn't imaginary and isn't a personal failing. Real biological processes, with insulin among the most important, affect whether stored fat gets released and burned. When insulin is elevated, fat release slows down. That's basic physiology. Second, behaviors exist that can influence this system. Eating protein and vegetables before carbohydrates, taking a short walk after meals, possibly limiting your eating window. These approaches have research support for reducing blood sugar and insulin responses. Third, none of these are silver bullets. The most carefully controlled studies tend to show that what you eat, and when you eat, it have more modest effects than the total amount you eat. Understanding insulin doesn't give you a shortcut. What it gives you is a more complete picture of what your body is doing. And when you understand the system, you can make more informed decisions about how to work with your biology instead of against it. You're not fighting your body when fat loss feels difficult. Your body is doing exactly what it evolved to do given the signals it's receiving. The question is how to shift those signals gradually in ways you can actually sustain. That's less dramatic than a trick, but it's much closer to how this actually works.